From here, we're continuing our discussion of thermodynamics and adding in this idea of free energy. Now, we'll get to some definitions for free energy and whatnot in a few later videos, but just to kind of frame where we are and what we're about to go into, everything that we have done so far has been related to the first law of thermodynamics, which, remember, is conservation of energy. So you can't create or destroy it. The only thing you can do is transfer it from one form to another. And what we are getting in now is the second law of thermodynamics, which I'll give you some official words in a little bit, but second law of thermodynamics is that you can't win or break even in an energy transaction. And I have an example that is hopefully a familiar example to you, but as you start to read about this in other places, sometimes this is called a heat tax. So basically, it's a tax on your energy transaction, and you lose some of it in the form of heat. So we don't actually, right, we're still not destroying energy. It just got converted to a potentially non-usable form as a tax in our transaction. So an example of this would be something like a rechargeable battery. And I'm not going to attempt to draw this, so I'm just going to write rechargeable battery. And let's say that you use that battery to power something, and it does 100 kilojoules of work. And you use up the entire battery, so in the end, what you have is a dead battery. Now, it's rechargeable, so you can charge that battery back up. And if you've ever done this, when it's plugged in, you can feel that the batteries get warm as you do this. So the thing is that to go back from a dead battery to a charged battery, it takes greater than 100 kilojoules to recharge, because some of that energy is lost as heat. So this is what the second law of thermodynamics is telling us. Now, we will get into some other definitions that will help you make decisions about what is going on in your reaction and actually determine something about whether or not the reaction is thermodynamically favorable. So I'm going to write this question: is the reaction thermodynamically favorable? And I'm also going to add on here the more common term. So rather than saying thermodynamically favorable, in many, many cases, you will see the word spontaneous, which is not quite right as a term for what we are talking about, but historically, it's the one that's been used the most, and the things that you will see out there as you do reading will still say spontaneous when what they really mean is thermodynamically favorable. So this is the goal of all of thermodynamics, is to get information about a reaction and then determine whether or not it is favorable or spontaneous. So what we mean by that is that if you have a favorable or spontaneous reaction, it means that the reaction occurs without ongoing outside intervention. So as an example, no, it's not a reaction example, but it's hopefully one that will help you conceptualize what's going on here. Something that happens spontaneously is if you take a book and you drop it in a gravitational field, it will fall to the ground. You don't have to push the book down it will fall without ongoing outside intervention. So a not favorable or a non-spontaneous reaction as you can imagine, requires outside intervention. So in the case of our book example, would be lifting the book back up to a higher place. If you stop applying that outside intervention, the force that you're using to lift the book, it falls again. So the reason that a lot of people have changed their language to talk about favorable versus not favorable is because spontaneous can sometimes be confused with how quickly a reaction goes. So big stars, do not confuse spontaneity with speed. When we determine whether or not a reaction is thermodynamically favorable, it says absolutely nothing about how quickly that reaction happens. So there are a lot of spontaneous reactions that are really slow. There are a lot of non-spontaneous reactions that as soon as we put in that outside intervention, go really quickly. So I'm just going to say a spontaneous reaction can still be slow. So in general, so obviously I'm going to give you some generalities and then give you the exceptions, and we'll talk about why these are happening. So generally, we see that an exothermic reaction, if you remember, that means our delta H reaction is negative, is a favorable or a spontaneous reaction. And an endothermic, so delta H greater than 0, is a non-favorable. That usually makes logical sense when you think about it, right? Remember these exothermic reactions, when you look at the energy diagrams, look downhill. The endothermic reactions look uphill. However, here are some exceptions. So, ice melting above 0 degrees Celsius, sodium chloride dissolving in water or dissolving in any polar solvent that it'll dissolve in, and the evaporation of any liquid. So in this case, I have ethanol going from a liquid and turning into a gas. So these are all endothermic and spontaneous or favorable. So in all of these cases, we have to put in energy to get these to go, right? They're endothermic reactions, uphill reactions, but they are favorable. These are all things also that you have observed happening, right? When the temperature gets above 0 degrees, ice will melt. We didn't have to do anything extra to get the ice to melt. If you put salt into a cup of water, it's just going to dissolve. If you had a puddle of ethanol sitting out on a bench or on the floor, it would just evaporate on its own. The thing that these have in common, so we'll say commonality, is that they have an increase in something called entropy. And I will do my best to enunciate this, but I guess the benefit of having this in video lecture is that you can see the word written out. We now have to deal with enthalpy and entropy. And in this case, the thing that it has an increase in is entropy. And another way that we talk about entropy is that it is an increase in disorder. So everything gets messy as the universe proceeds in the direction that it wants to proceed. And so an increase in entropy helps make these reactions favorable. And we'll look at that mathematically, and we'll also talk through a couple more examples. So as a definition, entropy, which we use a capital letter S to talk about entropy, it is a measure of the dispersion of energy in a system. Which, okay, and that doesn't mean too much to you probably. As I said, we like to talk about this as disorder. So more disorder equals more entropy. And as you look for examples of this, right, the super common example is to show something like a barn that's in really good condition, and if you just leave it out to exposed to the elements and you don't put in outside ongoing intervention, everything goes to crap and falls apart. And so this is an illustration. The way that the universe moves forward is that essentially everything goes to crap. So this is what the second law of thermodynamics says officially. So second law of thermodynamics, for any thermodynamically favorable process, this is going to take me forever to write, thermodynamically favorable. You can see why people like to stick with spontaneous. Reaction or process. The entropy of the universe increases. So delta S of the universe is greater than 0. Well, let's get this. The word increase is actually in here. Great news for us. This is a state function. So we don't care how you get there. All we need to know is the beginning and the end. So second law, if it's spontaneous, entropy of the universe increases. So a chemical system proceeds in the direction that increases the entropy of the universe.